Alright, today we're going to be talking about logarithmic functions, and the best way is to jump right in and start looking at them. Now, first things first, the discussion that we're going to be talking, the thing we're going to be talking about today is going to be based on our work with inverse functions back in section 1.8. Now, if you're not clear on inverses and things like that, you need to go back and review section 1.8, whether in your book, videos, or whatever. But here's a summary of what you should already know about functions and their inverses. Only a function that is one-to-one will have an inverse that's also a function. A function f has an inverse function, and it's written f to the negative 1 power, but that's not actually an exponent, it's notation, if there is no horizontal line that intersects the graph of f at more than one point. If you remember, that's where we talked about the horizontal line test. Now, we talked about the vertical line test. That's to determine whether or not a relation is a function. Well, once we know a relation is a function, we can use the horizontal line test, and if it passes it as well, that means we're going to know that it is going to be a function also. Now, if a function is one-to-one, then its inverse function can be found by interchanging the x and the y in the function's equation and solving for y. Now, if f of a equals b, then f inverse of b equals a. All this is saying, this is just a mathematical way of saying that the x and the y change positions on the inverse. So if you have the point AB on the function f of x, then BA is on f inverse. That's all that it is. So you just swap the x's and the y's, and then that's going to be a point on the inverse of the function. Now, it also means that since you're changing all the x's and all the y's, the domain of f turns out to be the range of f inverse. And the range of f is the domain of f inverse. Remember, the domain or the x values are the input values for the function. The range are the output values for the function. So we just swap those two, and we've got the inverses domain and range as well. All right, if you do the composite of the function and its inverse, you're always going to get x. If you remember, this was one of the ways, or this was the way that we actually tested to see whether two functions were inverses. If you took one function and put it in place of x and the other one, and it simplified down to x, that proved that the two expressions, or the two functions that you were dealing with, were inverses of one another. And it does not matter which way you do it, whether you do f inverse into f or f into f inverse. You should still get x with both of them. Now, the graph, when we look at the graph of an inverse function, it should be a reflection of the graph of f across the line y equals x. So those are the things that you should remember about inverse functions from section 1.8. And like I said, if you don't, go back and look at section 1.8 and make sure you're good with it. At least these things, because those are very, very important concepts for inverses. Now, the definition of the logarithmic function says, for x that is greater than 0 and b that is greater than 0 but not equaling 1, y equals log base b of x is equivalent to the expression b to the y power equals x. The function f of x is equals log base b of x is called the logarithmic function with base b. Now, here's the thing, you got to remember this. The equations are different ways of saying the exact same thing. The first equation is in logarithmic form, the second's in exponential form. Notice that a logarithm, y, is an exponent. If you look at these two examples, what you're doing is you're finding what power b had to be raised to get x. So when you do a logarithmic expression, you're looking for a power. You're looking for an exponent. Now, there is a little trick that I use when I'm taking these back and forth. I do a little spiral, b to the y power equals x. And here, there's not really a good one, but the base is always the base. B is b. Base of the exponential is the base of the log. And then the x and the y just swap positions. The x goes over to be with a b, the y goes over to be on the other side by itself. But the relationship is, anytime you take a logarithm, you're actually solving for what exponent you would have to have. What exponent this base would have to go to equal the x. Alright, so the location of the base and the exponent and exponential and logarithmic forms. In logarithmic forms, the base is the base is the base. Same thing with both of these. The base is the base. The exponent is equal to, is what's equal to the log. Once again, because a log function finds the exponent. And then over here, b is the base and y is the exponent, and it equals x. Now to change from a logarithmic form to the more familiar exponential form, I just showed you, b to the y power equals x. Now we're more comfortable with this, and we can think more about this because this is kind of new to us. We may have seen it, we haven't worked with it a whole lot. Alright, so let's write each of these equations in its equivalent exponential form. Alright, so if I do 5 to the second power equals x, I can go ahead and simplify that and do 25 equals x. If you were solving it, that's what you could do. Alright, and here b to the third power equals 64. And here, even though the equals is on the other side, it still works. You're going to start with a base, go across the equals, then come back across. So 3 to the y equals 7. So that's all you're doing. Now, you don't always have to simplify it, but if you can, it's always a good idea to do that. And here, what would you raise to the third power to get 64? Well, we could find that b is equal to 4. You can take the cube root of both sides. 4 times 4 gives you 16. 16 times 4 gives you 64. So once you get it into exponential form, it's a little easier to solve from a log function. You're not always going to see it right off the bat when you do a log function. You will the more you do them, but you're not going to always see it. Alright, you guys pause the video and try these. Just rewrite them. Don't worry about simplification unless it's just really, really easy to do. And I want you to try those, put them in exponential form, and I will show you the answer in 3, 2, 1. Sorry, just kidding. This is actually going from exponential to logarithmic. It's the other way. So the thing is, the base is the base, so I know I'm going to have log base 12. 2 is my exponent, so remember for a log expression, it's the answer, and then I'm taking the log of the other side, x. So here, what's my base? My base is going to be b, so log base b, and my power is 3, so So it's going to be over on the other side, and I'm taking the log of 8. Okay, here, base is the base. The base of the exponent is the base of my log. And then the e and the y are on the same side, so I'm going to swap them. That goes to the other side, and I'm taking the log base e of 9. Now that's a special thing we'll talk about later. So not quite as straightforward going from the exponential to the logarithmic, but it's not that difficult. Get your base into the base of the log and then swap the two things on the side. Here the 2 was with the base 12. Well, in the log, notice it's on the other side of the equal sign. And then so those two things are going to, the exponent and the answer is going to swap places. Right, so now let's evaluate some logarithms. Remember, all a log is doing is finding what power you have to raise the base to get this answer right here. So what power would you have to raise 2 to get 16? Well, it's going to be 4. All right, now this one, and here's another way that you can go about doing this. You can actually take this and think about it and say, let's see, what is this as an exponential expression with a base of 2? So 2 to the what gives me 16? Well, it would be 2 to the 4th. So the log base 2 of 2 to the 4th, and what exponent is it? Well, it's 4. And we'll explain a little more of why that works later when we start looking at some of the properties, but that's another way of thinking about it. Here, we've got a number on the bottom. Remember, what do you do to make it go to the bottom? You use a negative exponent. So that means you're asking 7 to what power gives me 49? Well, that would be 2. If you square 7, you're going to get 49. But since it's on the bottom of the fraction, that 2 needs to be negative. And here's why. Just make sure that you know this. 7 to the negative 2 equals what? Well, 7 to the negative 2 is the same thing as 1 over 7 squared. Remember, that just means it's going to, the negative exponent means it's going to move to the bottom. And then what, of course, is 7 squared? 49. So we can always go back and do the exponent, the exponential form, and check to see if we get the right answer. Now, remember, our answers can be any real number. So when we're looking for powers, it can be any real number, including fractions. So what would you do to 25 to get 5? Well, you would take a square root, right? Take the square root of 25, you're going to get 5. What fraction means to take the square root? Well, the exponent 1/2 means that you're going to take the square root of something. So that's where that answer comes in. Now, this is one of those where that was like what we're talking about over here. Write this as an exponential expression, this part right here, and then just take and use the exponent. As long as the bases match, what fractional exponent would I use to express a 5th root? Well, it'd be 1/5. I don't know why I'm writing 2. It'd be 1/5. So now, if this base and that base match up, then that's just our answer. So it's 1/5. Because remember, what are we asking? If we have log base 2 of 2 to the 4th, I'm saying what power do I have to raise 2 to get 2 to the 4th? Well, I've already got the power right there. So I don't have to figure anything out. I already know what power I have to raise this base to get this number, the 4th power. As long as those bases match, the exponent is the answer. All right, I want you guys to try these and see what you can come up with. I want you to pause the video, try them without cheating, try them without looking at anything, and see if it clicks and make sure. That's very important. So I'm going to show you the answers. You pause it, work the problems out, and then you can come back and look at the answers and see if you got the right answers. I'll show you the answers in 3, 2, 1. All right, so here are the answers for these problems. Log base 10 of 100. We're saying 10 raised to what power gives us 100? Well, if you square 10, you're going to get 100. So that's the answer, 2, that exponent. With part B, you're saying 5 raised to what power gives you 1 over 125? Well, once again, just worry about the bottom. What power would I raise 5 to get 125? Well, 5 times 5 is 25. 25 times 5 is 125, so third. But since it's on the bottom of the fraction with a 1 on top, I've got to make that 3 a negative 3. What power would I raise 36 to get 6? Well, I know that if I take the square root of 36, I'm going to get 6. So that would mean that I would have to raise it to the power of 1/2. And this one, of course, I can rewrite that as 3 to the 1/7 power. So the log base 3 of 3 to the 1/7 is just going to be, remember, when I do a log, I'm looking for what power, so it's 1/7. Now, some basic properties of logarithms that involve 1 is this one. The first one here, log base b of b equals 1. As long as these two numbers are the same, it equals 1. Because remember, what are we asking? We're asking what power do I raise this base to get this number right here. So b to the first power equals b. Therefore, the answer is 1. Now, if I take the log base b of 1 and it equals 0, no matter what value of b is, what power can I raise it to and always, always, always get 1? Well, remember, any number raised to the 0 power except 0, which we can't have a log of 0 anyway, is equal to 1. So you can always go back and check. 2 to the 0 equals 1, 4 to the 0 equals 1, 10,000 to the 0 power equals 1. So no matter what the base is, this property holds true. Looking at the exponential values of that. All right, so what do we know using those properties? What do we know about the first one here? Log base 7 of 7 is going to equal 1. Log base 5 of 1, what power do I raise 5 to get 1? Well, it'd be 0. All right, now, inverse properties of logarithms. Remember, we've talked about the exponential expression, the exponential function, and we've talked about the fact that we have the inverse expression of it is the logarithm. Well, that means that they have ways that they cancel each other out. Here's one of them. We take the log base b of b to the x. We talked about this one just a second ago. Since these match, this is the power. And the other one is that if we have an exponential and we have a log of the same base as this exponential in the exponent, then those are going to cancel out and give us x. Guys, these are very important for you to remember because we're going to use these to actually solve some problems. So just to give you an idea, if we have the log base 3 of 3 to the 5th power, then using this first property here, the answer is 5. Using the second one here, if we had 3 to the log base 3 of 5, then the answer is 5 again. 3 exponential to a log base 3 cancels each other out and leaves you with just the 5. A log base 3 of an exponential with a base 3 cancels each other out and leaves you with 5. It doesn't matter. It doesn't have to be just 3. It can be anything. That's why we've got these b's here. As long as these two match, this works. As long as these two match, this works. But the bases of the two expressions must match. If you have the log base 2 of 3 to the 5th, it does not equal 5 because my bases of my log and my exponent do not match. So, no. Alright, so with the properties right there above it, I want you guys to try those real quick. It shouldn't take you long. Just pause the video and see what you come up with, and I'll show you the answers in 3, 2, 1. Alright, so here are the answers. Log base 4 of 4 to the 5th. Remember the log base 4 and the base exponent of, or the base exponent, the exponential with a base of 4 will cancel each other out to leave you with just 5. Same thing over here. If we have 6 to the log base 6 of 9, the exponential with a base of 6 and the log with a base of 6 cancel each other out there, and that's just going to leave you with 9. Alright, now we're going to graph f of x equals 2x and g of x equals log base 2 of x in the same rectangular coordinate system. Now this is really easy because we've already done the 2 to the x, but let's go ahead and we're going to make a table again. X and f of x. We're just another way of saying y. And we're going to use the same general numbers we were doing before. I'm not going to use the 3's and the negative 3 though. I'll just do 2, 1, 0, 1, and 2. 5 points will be enough to give us an idea. So for f of x, it's 2 to the x, so 2 to the second power gives me 4. 2 to the first power gives me 2. 2 to the 0 power gives me 1. 2 to the first, negative. 2 to the negative 1 power gives me 1/2. And 2 to the negative 2 power gives me 1/4. So when I plot these numbers, 0, 1, negative 1, 1/2, negative 2, 1/4, 1, 2, 2, 4, and of course 3, like we did before, it's going to be up there at 8. So when I graph this, nice smooth curve, and it's going to approach 0, because remember 0 is an asymptote, y equals 0 is an asymptote for this thing. Too straight up. So there is f of x. Now, when we go to graph log base 2 of x, what do we know about that? Remember, it's the inverse. So g of x is equal to f inverse of x. And what do we know property-wise of the inverses? Well, the inverses, remember, if AB is on f of x, then BA is on g of x, or let me write that as f inverse. And since g of x is f inverse, then all we have to do is take every one of these points right here and swap the x's and the y's. So when I go to graph this, instead of 2, 4, I'm going to graph 4, 2. I go over 4 and up 2. And then instead of graphing 1, 2, I'm going to graph 2, 1. And instead of graphing 0, 1, I'm going to graph 1, 0. And instead of graphing negative 1, 1/2, I'm going to graph 1/2, negative 1. And instead of graphing negative 2, 1/4, I'm going to graph 1/4, negative 2. So hopefully you can kind of see that shape now. I'm going to come up And then also, don't forget, I have this one right here that's 3, 8, so I would have 8, 3. So I've got a point right there. So there is my g of x, which is also f inverse of x. So this is log base 2 of x, and this one is 2 to the x. So all we had to do to get the graph of a log is take the graph of the exponential and swap them. Now remember, we've got, what do we know about the graphs of these things? Not just the individual points, but the graphs. Well, we also learned and talked about at the very beginning that we rotate, or that we reflect across the line y equals x. Well, there is that line right there, y equals x, and you can see that if you folded it across that line, these two graphs are going to line up. That's what we mean when we reflect across a line. So you should be able to do a log base 2, a log base 3, those basic ones. Nothing, I'm not going to get crazy and do a log base 5 or anything, but you should be able to graph a log base 2 and a log base 3 using the exponential that we did in the previous section, and then just swapping your points. Now I'm going to want to see the points and all that stuff, so make sure you show me all that information. All right, some characteristics of the logarithmic functions of the form f of x equals log base b of x. These are the domain, range, and all that stuff. The domain of f, this is for the base graph, not any transformations, remember, same way we did with the exponential. The domain of f of x equals log base b of x consists of all positive real numbers, not including 0, notice, but you cannot take the log of a negative number. You cannot take the log of a negative number. You need to get that through your mind and make sure you wrap your head around it. You cannot take the log of a negative number. That's a huge domain limitation when you're dealing with logs. The range of f of x equals log base b of x consists of all real numbers, negative infinity to positive infinity. So you cannot take the log of 0, and you cannot take the log of a negative number. And guys, make sure you're understanding what I mean here. I'm not saying you can't get, if you've got y equals log base 2 of x, I'm saying numbers here, no negatives, and no 0. Over here, all real numbers. So the y value can be all real numbers. The x that you're taking the log of, you can't take the log of a negative and you can't take the log of a 0. Not only that, don't forget that your base is going to be non-negative, or let's just say no negatives and not 1 and not 0. So there are rules with logs that have to be true. You've got to know these, because otherwise you're going to go in and you're going to try to take the log of a negative number and you're going to be bumfuzzled when your calculator keeps giving you errors over it. Well, that's one of the rules of logs. You cannot take a log and get a negative number. You cannot take the log of a negative number. You can take a log and get a negative number as your answer, but you can't take the log of a negative number. And it goes back to what we talked about in the last section, where, remember, if we have a base of 2, is there any number that I can raise this to and get a negative number? Well, there's not. And remember how this is. Now this is log of base 2 of this number right here, negative number, equals x. Well, once again, if you can't, there's no way, there's no power you can raise 2 to get a negative number. That's why this is never going to equal. That's why. Now the graphs of all logarithmic functions of the form f of x equals log base b of x pass through the point 1, 0, because f of 1 equals log base b of 1 equals 0. And notice that is the key point. That's the inverse of the key point 0, 1 on the exponential function. So the x-intercept is 1 and there is no y-intercept. Now if b is greater than 1, f of x equals log base b of x has a graph that goes up to the right and is an increasing function. If b is between 0 and 1, then log base b has a graph that goes down to the right and is a decreasing function. Remember, both of those, when you graph those, they're just inverses of the exponential function. So if you can do the exponential function of that base, then you're good. Because all you got to do is swap your x's and your y's. The graph of f of x equals log base b of x approaches but does not touch the y-axis. The y-axis, or x equals 0, is a vertical asymptote. So as x approaches 0 from the positive side, log base b of x, the y value, is going to approach negative infinity or positive infinity depending on what value b is. Alright, now here are the transformations involving the logarithmic functions, and big surprise, guess what? They're the same transformations we've had since the first chapter. So I'm not going to go through and talk about all these. We can ask questions if you've got them in class, but you should not have questions on these at this point. You should be able to do a plus c or a minus c after the outside of the log transformation. That's up or down. A plus c or a minus c inside the log. That's a side to side. Reflections are going to be the same. Vertical shrinkings are going to be the same. If it's outside, a value of c is going to stretch it vertically. If it's greater than 1, it's going to shrink it if it's between 0 and 1. Exactly the opposite here, except you're going to do horizontal. Horizontally, it's going to shrink if c is greater than 1, and horizontally it's going to stretch if the value of c is between 0 and 1. All these transformations are, this exact table actually is in your book on page 405. Don't copy this down. We've copied this table down enough. But you should know how to apply them. Now, in section 3.1, we learned that the domain of an exponential function of the form f of x equals b to the x includes all real numbers, and its range is a set of positive real numbers. Think about the graph. Guys, correlate what we're talking about here. Correlate how the exponential graph looks when we're talking about this. What x values can we have? Any number we want to. Therefore, the domain is all real numbers. What values of y can we have here? Well, we get down really, really close to 0, but we can go up to infinity. So 0 to infinity, not including 0, which means that what? The range is the set of all positive real numbers. All right, now, because the logarithmic function reverses the domain and the range of the exponential function, the domain of the logarithmic function of the form f of x equals log base b of x, that's the base log, is the set of all positive real numbers. When I say base log, I mean it has not been given any transformations. Thus, log base 2 of 8 is defined because the value of x is the logarithmic expression 8 is greater than 0, therefore is included in the domain of the logarithmic function f of x equals log base 2 of 8. However, log base 2 of 0 and log base 2 of negative 8 are not defined. We talked about this just a second ago. Because 0 and negative 8 are not positive real numbers, therefore are excluded from the domain of the logarithmic function. So it goes back to that exponential function. And its limitations of the range, which transfer with its inverse to a limitation of the inverse's domain. That's why we had the limitations on the domain of the logs, because of the limitations that were on the range of the exponentials. So in general, the domain of f of x equals log base b of g of x consists of all x for which g of x is greater than 0. Now, there will be differences when g of x has transformations built in and things like that. That's going to change. We're talking base graphs right now. All right, so let's find the domain of the log base 4 of x plus 3. Now, I'm going to show you a little trick here. What do we know? Let's go ahead and circle this. What do we know the blob or the circle thing here has to be? We can only take logs of positive numbers. So that means that x plus 3 must be greater than 0, right? So that's my g of x. X plus 3 is my g of x here. So to find the domain, solve for x. We're going to subtract 3 from both sides. So x must be greater than negative 3. Don't stop there. I want you to go back and double check. Check some value that's close to negative 3 but still greater than that. So let's say negative 2. If I plug a negative 2 right here, what's negative 2 plus 3? That's 1. Can I take the log base 4 of 1? Yes, it works. Can I take the log, if I plug in negative 3, what happens? So negative 3 plus 3 gives me 0. I can't take that, but that's not included in my domain, so I'm probably good. But that's how you find the domain. Remember what property this has to be, what it has to stay as, set it as an inequality, and solve the inequality. Okay, you guys try this one real quick. And I'm going to pause the video, and I'm going to show you, and you try it. Sorry, you pause the video, try it, and then come back and I'll show you the answer in 3, 2. All right, so here is the answer, and I went ahead and showed you the work and also expressed it in domain interval notation. So we know that x minus 5, this part right here, must be greater than 0 to be able to take a log. So all I do is I solve for x, and x must be greater than 5. So those are the only values that x can be, are values greater than 5. So therefore the domain is from 5 to infinity, not including 5, so I put parentheses. Remember, if it was including 5, I'd have a bracket there. And you never include infinity because it's not actually a number. All right, so here are properties of common logs. And we've talked about all these, so I'm not going to, we've talked about all these, so I'm not going to go over them again. I do want to introduce the whole common logarithm thing. You're going to see on your calculator a button that just says LOG, and that is called the common log. The common log is a log base 10. The log base 10 is understood. So if you see LOG, it is understood to be a log base 10. That one you don't have to write a base for. So if you just write LOG of x, that is understood to be a log base 10 of x. So, and that's the common log. Common logs are used in a couple of different things. They're used in the Richter scale, where they measure earthquakes. They're used in the decibel scale, where they measure sound pressure. A lot of the things like that are base 10s, and you're using a logarithmic scale. So when you just see LOG of something, you're taking a common log. Now, natural logs are logs that we talked about earlier with a base of e. Remember, we talked about e in the last section being 2.7182812 whatever. Anyway, that's what e is. And a log base e of x has the special notation of ln of x. Now, the reason it's backwards here is because is probably because it's Latin or Greek, and you have logarithmic natural or whatever. I don't know for sure, but that's the notation we use. So log base e is the natural log, or ln. To find the domain of these, nothing is special. This is still a log, so we know that this thing right here must still be greater than 0. So 3 minus x must be greater than 0, and that means we're going to move the 3 over. We have negative x is greater than negative 3. I've got to find what x is, not negative x, so I want to divide both sides by negative 1. Well, remember what happens with your greater than or less than. It has to flip over. So now my domain is all values of x that are less than 3. So your domain would be negative infinity up to, but not including 3. Now with this one, what do we know about these values here? No matter what value we have here, it's not, when you square it, it's going to be positive. So x minus 3 squared must be greater than 0. But when you square it, guess what? It's going to be greater than 0 anyway. So all you're looking for to exclude is when this thing is equal to 0. Remember, any number that you square is going to be positive except for 0. So when is x minus 3 equal to 0? Well, when x equals 3. So in this case, x cannot equal 3, so the domain would be all, no parentheses there, so the domain would be all reals except x cannot equal 3. Because if you put 3 in here, you got 3 minus 3, which is 0. 0 squared is still 0, and you can't take the natural log or any log of 0. No, though. That's... Oh, that's right. All right, and here are the properties of natural logs. Hey, guess what? They're the same ones. So, except for the bases, remember bases is e, so we have to use those.